As of late 2024, the Peruvian government reported 2,476 paralyzed public works projects across the country. That represents $43.1 billion in committed, frozen capital. When auditors break down the causes for these massive delays, the data shows 25.4% are due to contractual disputes, and 21.2% stem from financial shortages. Only 10.9% are officially attributed to technical design flaws. Read at face value, that data suggests engineering mistakes are the least urgent problem for managers. But that conclusion relies entirely on an accounting illusion. To understand why, trace the chronological life cycle of a single structural defect. An error does not physically manifest on the day the blueprints are approved. It sits dormant for years, and when it eventually surfaces as a physical problem during construction, it triggers cost overruns, work stoppages, and legal battles. When that happens, the public recording system logs the failure based on its visible symptom, the resulting contractual dispute or budget shortfall, rather than the initial engineering error triggering the reaction. Relying on this symptom-based auditing means public infrastructure managers are consistently directing their resources and solutions to the wrong phase of the project's lifecycle. The field of quality management identified this dynamic decades ago. Theorists like Feigenbaum, Giron, and Crosby established the cost of poor quality, a framework calculating the exact volume of resources that evaporate due to entirely avoidable defects. They organized quality spending into 4 distinct categories: the cost to prevent an error, the cost to discover it, the cost to repair it internally, and the cost of an external failure after the project leaves the door. Because standard public accounting primarily tracks money as it leaves the treasury, it effectively ignores those first 2 proactive categories. By underfunding prevention and inspection, governments are forced to pay for their errors out of the final, most expensive category, external failure. For a quality cost model to actually work in practice, an organization needs an operational mechanism capable of tracing every single lost dollar directly back to the specific identifiable failure that caused it. Without a mechanism that ties financial hemorrhage back to early-stage decisions, public infrastructure governance remains unaware of its own systemic inefficiencies. This chart maps flaw origins versus manifestations. The blue bars show 48% originate during design, but the orange bars reveal only 4% are caught on the drafting table. The vast majority bypass review entirely, manifesting later, 48% in construction and 25% in operation. This chart illustrates the amplification rule logarithmically. Catching errors grows exponentially more expensive over time. Fixing a design error internally is our baseline, 1x. Discovering it in construction multiplies the cost by 10. At delivery, it's 50x. Undetected until collapse, the financial penalty multiplies by 1,000. This chart translates those multipliers for a $20 million project. A $260,000 oversight during design becomes a $5.1 million crisis at delivery. If it results in a collapse, the cost exceeds $100 million, consuming over 5 times the original project's value. Pouring budget into strict on-site construction supervision while skipping rigorous independent design audits is a reactive strategy. It mathematically guarantees budget overruns because it attacks the symptom rather than the origin. To translate these costs into managerial priorities, organizations use the risk priority number, or RPN. It calculates total risk by multiplying 3 variables: how probable the failure is, how severe its impact would be, and how difficult it is to detect. This heat map tracks RPN across a life cycle. Errors begin in design with high severity, but remain highly detectable, keeping risk moderate. As the structure is covered up, detectability plummets, causing risk to skyrocket. The highest risks don't occur when mistakes are made, they peak during operation. The managerial implication is precise. The most effective point to intervene is the earliest phase, where the error is still detectable at a low cost. By the time a failure hits maximum risk, intervention is already too expensive.
Standard risk models work perfectly for private manufacturing. A corporation can mathematically justify leaving a low-probability structural defect in place if the actuarial cost of paying future damages is cheaper than the immediate cost of prevention. But applying that same actuarial math to public infrastructure breaks the core mandate of the state. A government's primary function is protecting the lives of its citizens. That obligation cannot be reduced to an optimized cost-saving function. This requires a non-negotiable ethical constraint in the risk model. If a specific failure mode threatens human life, its severity variable cannot be averaged out. It must be locked at absolute maximum before the evaluation even begins, disabling the standard optimization curve entirely. Consider the Plasco building collapse. The structure was converted to an unauthorized use without updating its fire protection systems. When it caught fire, the result was a catastrophic loss of life, heavily impacting the first responders sent in to save it. In the Changsha self-built housing disaster, the root cause was the deliberate adulteration of inspection documents to provide cover for unpermitted expansions. Falsifying technical records renders the underlying risk invisible by neutralizing the detection alarms. The organization receives a signal that everything is fine precisely because the device meant to emit the alarm was intentionally silenced. Compromised supervision transforms the engineering problem into a governance failure, demanding immediate project paralysis rather than a technical recalculation. Knowing that costs amplify exponentially and governance failures neutralize early warnings, the direct question for public managers is exact: how much of the budget must be allocated to early-stage prevention to stop this cycle? This chart visualizes the leverage curve of preventative investment. Without a systematic prevention function in place, the cost of poor quality devours roughly 50% of a project's total production value. By allocating just 1 to 5% of the project cost specifically to independent design audits and model validation, the residual cost of poor quality drops rapidly into the single digits. Past 5%, the returns flatten out. This chart breaks down the two opposing systemic loops in public management. It starts with the spiral of reactive deterioration. When prevention budgets are cut to save money up front, latent defects slip through undetected. The cost of those defects eventually amplifies, depleting the available budget, which forces even deeper cuts to prevention on the next cycle. The virtuous cycle runs the exact same circuit in reverse. Early investment in prevention catches errors while they are cheap to fix. This lowers the latent risk, preventing amplified costs later and preserving the budget required to sustain prevention on future projects. Cutting the design audit budget activates a reactive deterioration spiral that will eventually bankrupt future budgets. This reactive cycle moves forward through sheer inertia, long after the original budget-cutting decision has been made. For the public manager, this analysis yields 3 precise operational directives. First, independent technical design review represents the single highest return on investment intervention available to a public manager across the entire project lifecycle. Second, public auditing systems must be completely recoded to track the actual origin cause of a budget overrun, rather than passively logging the visible symptom at the exact moment the capital freezes. Third, managers must acknowledge that technical safety models are powerless against governance failures. The ethical boundary protecting human life must be mathematically hard-coded into institutional risk assessments, so it cannot be bypassed by a cost-benefit calculation. Risk reaches its peak in the shadows. The danger is greatest exactly when the mechanisms designed to catch errors are compromised, bypassed, or underfunded. If the ultimate stakeholder of public infrastructure is the citizen, the metrics of success cannot be purely financial. True public value is only created when strict engineering rigor is governed by non-negotiable ethics.